So the antiderivative should be 80 thirds what? X, right? Because now x is our variable. Minus 2 thirds x cubed. And we're evaluating that from x. I don't really need to say x equals 0 to 2, but I may as well at this point. So 160 over 3. So I'm plugging in my two values. When I plug in 0, I get 0, don't I? Okay. Okay, so I get 160 over 3 minus 2 cubed 8 times 2, 16 over 3. So 144 over 3. That go in there? It does, doesn't it? 48? 48. That's very odd that that's a nice number like that. The volume of that solid is 48 cubic units, whatever, we don't know what it is. It could be cubic inches, cubic feet, cubic meters, could be cubic miles. Yes?
So here we actually had, definitive points. But
You mean like 0 to 2, 0 to 2?
Yeah.
Uh-huh.
But oftentimes we face with just integrals by themselves, so we have constants.
Oh, you mean like if you wanted to do an indefinite double integral?
Yeah.
Yeah, you wouldn't. We don't really do indefinite because we're not trying to just find a general antiderivative of these things, because when it comes to a double integral, you have an inner and an outer, right? So you'll always be able to do just the same thing you did in Cal 2 because you're just holding one of those variables constant. Okay? So we don't need to do indefinite integrals. Good question. The bigger question for us is going to be, what if our region on the ground isn't a rectangle? Does the formula still work? And the answer is no. Okay? We have to change things up a little bit. So, all right, good on this? What if we reverse the order? Like there we did, what integral was on the outside? We did with respect to what on the outside? X, and on the inner one was with respect to y, right? What if we would have reversed it and did with respect to x first, then with respect to y? Do you think it would have changed our answer? No. It shouldn't, but there has to be a theorem that says that we can do that, and this is it. Fubini's theorem. It says that if your function is continuous, meaning that it's nicely behaved sheet function up here, and you have a rectangle, A to B, C to D, that the order does not matter. You can do the inner one with respect to x, outer with respect to y, or inner with respect to y, outer with respect to x, and you will get the same answer. Okay? Now, that's the theorem. That just, it says we can do it, but I want us to do this one right here. And I'm going to give you a second to see if you can't use what we've talked about. I'm going to step out real quick. I got a call from someone that never calls me, and it might be an emergency. So they've called twice and texted once. So It was not an emergency. I'm going to start writing it down. You can continue. Oh. How many of you got to that part? At least you know what's going in here, yeah? I think I'm ready to talk about it. Can we talk? So we're trying to find the volume under that surface. Okay, so we need to know what R is, the region on the ground. Everyone clear? X between 1 and 2, Y between 0 and pi. So we're trying to find the double integral over the region R. Here's our surface, right? That's our height, and then we're multiplying by the little area patch on the ground. That'll give us the volume of each little rectangle, right? We replace the function of xy with our function of xy, dA and r. Now, I'm ready to get it in terms of x and y. So I have two options, don't I? Because this is a rectangle, I can do it one of two ways, can't I? I'm going to show you both. Okay, so I can do option 1. Let's go option A. And let's go option B. Now, in the last problem, I didn't give you options, right? But let's take a look at the two options we have here. The first option, I can go, let's say, like we did last one, dy, then dx. The other option, I go dx, then dy. Fubini's theorem tells me I can do this because it's a rectangle. Now, if I do this option, the function goes in here, just like this. Right? And what would my limits of integration be here? So the inner integral would be what? 0 to pi. And the outer integral would be 1 to 2. Okay, here it would be the other way. 0 to pi on the outside, 1 to 2 on the inside, but this doesn't change. Okay. So in many cases, it really doesn't matter which one you do because they both give you the same answer. But, which of these would you rather do?
I'd rather do dx.
You'd rather do dx first?
Uh-huh.
Why?
Because if we did dy first, we have two variables multiplied together, which that's a little bit more complicated than just where y is a constant.
Yeah, a lot bit more, right? How are you going to find the antiderivative of this if you got a y out here and a y inside? What would you use?
Integration by parts.
Integration by parts. You'd use integration by parts. Because that looks a lot like, if I were to ask you to integrate this, y sine of 4y dy, right? If I were to, so we're treating the x like a constant right now. If I ask you to integrate this, this would be integration by parts. Who wants to do integration by parts? If we can do this way. See here, if we do this one, x is the variable, y is a what? Constant. So that would be like integrating 2 sine of, I don't know, 2x? Something like that? What would you rather integrate? This with respect to y or this with respect to x? This, for sure, right? For sure. So again, either way, you're welcome to do. But this one is just much easier. So I'm going to continue with this one. All right? So when I do that, so no, because of integration by parts. When I do that, let me continue over here. So this is going to be outer integral 0 to pi, okay, bracket. All right. What would the antiderivative of this be? Negative cosine of xy. Done, right? That's what it is. That's what it is. Treat your y like a constant. Then you can ignore it here, can't you? Okay, what's the antiderivative of sine of, imagine that that's a 3. So what's the antiderivative of sine of 3x? Negative cosine of 3x, but then you have to divide by 3, right? Or scale it. So the antiderivative of sine of xy should be negative cosine of xy, but then divide the whole thing by y. And then that kills off the y that I was just hiding. So I have to trust that you can get from here to here, given enough time to think and reflect on it. Okay, that's our antiderivative, and then we're going to evaluate it from, okay, we're using x, right? So x equals 1 to x equals 2. And then once I'm done with that, then I'll come in here and I'll go with respect to y. Okay, plug in 2 for x. You get negative cosine of 2y. And then subtract from that negative cosine of plug in 1, y. Once we're done with that, we'll go with respect to x, right? No, wait. With respect to y. Okay. Let's clean that up. That looks bad in there. 0 to pi. That's just,
You can do cosine y.
yeah, can I just do cosine y minus cosine 2y? That all right with y'all? Just change the order of them, right? That becomes a positive cosine y. This is a minus cosine 2y. Just switch them so it's easier to look at. And can you integrate those with respect to y? Yeah, I hope. Yes. What do we got? Time for the antiderivative.
Sine y.
Sine y minus
1/2.
1/2 sine 2y. And then I'm evaluating that from y equals 0 to y equals pi. Sine of 0 is 0. So all the zeros should kill off, right? So it's really the pi is the only thing that really matters. But I still like to do this. I'll put 0 here. When I plug in 0, I get 0. But pi. Okay, sine of pi is going to be 0 minus 1/2. Wait a minute. Hold on. Shit. Hey, it's all 0, isn't it? What the hell? 0, 0. How are we getting a 0 volume? How do we have a 0 volume? Yeah, so go back to Cal 2 for a moment. Go back to Cal 2. In Cal 2, if I gave you the sine function, let's say this is y equals sine x, and I ask you for this right here, what would your answer be?
It cancels out.
It cancels out. So back in Cal 2, what's happening is that when you do the integral like this, it's taking the net area. It counts anything above the x-axis as positive, and it counts anything as below as negative. Why? Why? Because we're like, areas are always positive. Because remember, these rectangles, right, in here when we were doing those sums, right, the height of the rectangle is what? The value of the function. The width is always positive. So if your height is positive and your width is positive, it's going to be positive area. But if you're down here, your rectangle looks like this, then what's the height? The function's value, which is below the x-axis. So it counts that as negative times the width, which is positive. That means that it's counting the area as a negative. So they offset each other. Same thing happens here. The same exact thing can happen. We can have a surface that cuts through the ground, the xy plane. Any volume below the xy plane is negative volume. Anything above is positive, as the image that I'm about to show you will illustrate. Oh, before I show you it, how do we resolve that back in Cal 2? If I really wanted to know like the true area of this together, how would you do it? You do what? 0 to pi. Exactly. You would go, okay, change it. Let's go from 0 to pi, right? Get that answer. And then just double it, and that would give us like the true area, right? So we have to figure out where that function, what, has an x-intercept, right? Which would be pretty easy with sine x, right? To set sine x equals 0, you know where the x-intercepts are. For us, we would have to do something similar, right? We would have to do something similar. And getting old freaking sucks. You know how you always hear people say that? Trust me when I tell you this. It just like hurt my arm just erasing the freaking board, man. It's stupid. All right, so let's see here. Here's the surface we were just looking at. Okay, there it is. Whoa, it's crazy looking, right? Waving around, up and down. Okay. If we just plug in the things from that box in there, can y'all see it? Make it a little bigger. That's just the rectangle plugged into our surface. Let's go ahead and figure out what this volume looks like. Let's get all this shit out of here. Okay, there it is. So we were trying to find the volume of that. Do y'all see that there's some of it is above and some of it is below? And so how would we determine, what's above and what's below? See, we had our original rectangle. This was our R, right? And do y'all see this curve where the surface hits? It's like somewhere in here. On this, it's above, right? And on the other side, it's below. So we'd have to break it up. That's a curve, right? It's not a point like it was with the sine function. It was just, go from 0 to pi, right? It's not that. We'd have to do that. And do y'all see that this is no longer, this region here is not a box. And right now, we're rectangle, sorry. It's not a rectangle. And right now, we do not know how to do double integrals over anything other than rectangles. But what do you think's coming? Not rectangles, right? Okay, it's coming. This is the first section. So the answer being 0 is just telling us that this volume here is equal to that volume there. They offset each other. And notice also there's no symmetry here. Do y'all see that? There's not symmetry. Like the volume of this top piece, I would argue this volume here, this does not go as high, does it? This does not go as high as that one goes low, right? But this is a smaller little region. That's a smaller region. So even though it's lower, you get a lot of negative, it's a small little area. So this is a very odd problem, right? But we know that the net volume is 0. Fubini's theorem. Okay, so Fubini's theorem, this is an example. I'm not going to do this. This just says, here's a function, here's a rectangle. Do it both ways and convince yourself you get the same answer, okay? Just like we could have done the one we just did both ways, right? But it would have sucked the other way with integration by parts. I should show you this, even though I don't probably need to show you this, that if you go to Wolfram, you can do double integrals in here. You just do an integral, and then inside the integrand, you do another integral, like that. And so let's try it. Let's do, it was y times sine of x times y, right? And let's do that with respect to what was going to be hard, y first? Yeah. Then let's go with respect to x. And if we do y first, it'll go from 0 to what, pi? Let me see, I think pi, and then this will be 1 to 2. Okay, we should get 0. Yep, we got 0. Okay, so I had the computer do it the other way for us. Yeah, let's just leave it. How are we doing on time? Yep, let's see. Okay, so let's see where we are here. So Fubini, verify it. Okay, special case. All right, this is important. This will come up. We will use this a lot later. In random little places, this will pop up, and I'll say, remember that special case back in the very first section of chapter 12? This says, all right, let's say you're trying to do this double integral over some region of f of x, y, dA, right? This is the new thing for today, right? This gives you the volume underneath the surface. All right, let's say you're trying to do this. But in this special case that when you're looking at this, It's actually some function of x times some separate function of y. Okay? I should say this whole thing is. I want to give you an example right now so you can see it. So let's say we're trying to do this. Yeah, I'll do that. Let's say you're trying to do that dA. Do you see that this right here by itself is just some function of x? And this right here is some function of y, and they are separated from each other with multiplication. If you have that, if you can separate the x's from the y's through multiplication, then this says, okay, then you don't have to do any of this double integral stuff. All you have to do is do them separately, okay, and multiply the answers. So it says instead of doing that, what you'll do is you'll do the integral that has the x stuff in it. You'll do it with respect to x, and you'll use the limits of integration on x. You will multiply that answer times now you do the y stuff as a separate integral. So you can split it into two, all right? Could we have done that on the problem that we just did?
No.
The one where we had, what was it, y sine of xy? dA? Why can't we do it?
Because
You got x, y, and you can't rip this into two with multiplication. You can't get a product, right, where it's just y's and just x's. This xy is trapped, so you can't use this, all right? So there's the example right there. I can do this one pretty quickly. So we're trying to find the volume. If we set this up, we go sine x cosine y dA, right? That's what we're going to do. Now, I see that they're both, they both are, I'm able to separate those, right, with the multiplication. So what I'm going to do is I'm going to make this first an integral of the sine x dx times the integral cosine y dy, right? And then I just need my limits of integration, which are going to be my restrictions on x and y respectively. So 0 to pi over 2 here, and then 0 to pi over 2 here, right? And then whatever this answer is, right, I get that. Whatever that answer is, I get that, and then I multiply the two answers. So this is just back in Cal 2, separate them, okay? I'm not going to continue that, but you get the idea? Okay. All right, last thing, and we'll wrap it up. This will be a good breaking point for us. And then you'll have some homework to do here. I think this homework is going to feel pretty like, hey, things are good. Things are okay. Life's good. So some properties, some things that we can assume about double integrals. First one, as you might suspect, you can always pull a constant out of a double integral. Completely out of both, right? Just like you were in Cal 2, you can pull constants out, same thing. This next one says that if you have some surface, right, that is above some other surface, right? If this surface is above some other surface, then the volume under this surface should be bigger than the volume under that one. That's all that's saying. That makes sense visually? F is on top of G, then the volume below F should be bigger than the volume below G. All right, yeah, this is a good point right here. I think we can break, I don't know, 5 minutes. I don't want to rush through this part. So let's just stop here and we'll pick that up next time. All right? If anyone wants to follow me down to my office, I'm going to get the tests. I left them there. You can run down there with me and I'll be